Hello. In the previous lecture, we started a discussion on thermodynamics of polymer solutions. So, we discussed the case of an ideal solution and introduced the concept of lattice approach to calculating entropy change of mixing and Gibbs energy change of mixing. And then we started discussing the thermodynamic behavior of polymer solutions, and in particular we introduced the Flory-Huggins theory as the main theory that we will be discussing in this course for describing the thermodynamic behavior of polymer solutions. So, we in the previous lecture we covered the portion, the combinatorial entropy portion of this Flory-Huggins theory. So, in today's lecture we will continue that discussion and we will complete the development of this Flory-Huggins theory and the Flory-Huggins equation for describing polymer solution thermodynamics. Regards to the content of this lecture, we will briefly summarize the discussion from the previous lecture on the combinatorial term, and then we will develop another term which is referred to as a contact term, and this term basically accounts for the intermolecular interaction. So, if you remember in the previous lecture when we discussed the combinatorial entropy term, there the interaction was assumed to be absent. So, initially the change in entropy purely due to the different conformations that a polymer or polymer chains can adopt, that was considered, neglecting the effect of interactions. So, that led to the combinatorial entropy term, which will have a contribution towards the Gibbs energy of mixing. Today we will discuss another term which will account for the presence of intermolecular interactions between polymer chains and the solvent molecules. So, that will refer to as the contact term. And while discussing this contact term, we will also introduce a parameter which is called the Flory-Huggins interaction parameter. So, this parameter is an important measure of the solvent polymer interactions. So, we will introduce this and then we will complete the development of the Flory-Huggins equation to calculate the Gibbs energy change of mixing for a polymer solution. And after that we will briefly introduce the concept of partial molar properties, especially focusing on chemical potential, because it is an important property which is related to other experimentally measurable quantities as well. So, we will discuss that and we will see how the application of Flory-Huggins theory leads to certain expressions for the chemical potential as well as quantities like activity. So, the nomenclature that we introduced in the previous lecture, the same nomenclature will follow today as well. As and when some new term is introduced, the corresponding definition of that term will be provided whenever we encounter it. So, apart from all the terms that are listed here, we will be coming across some other terms as well during our discussion today. So, as and when such terms appear or such quantities appear, we will introduce them. So, before moving on with the discussion on Flory-Huggins theory and development of Flory-Huggins equation, let us just briefly summarize what we discussed about the Flory-Huggins theory in the previous lecture. So, some of the key assumptions involved in Flory-Huggins development of the Flory-Huggins theory are the first one is that it is a lattice based model. So, the model itself is a lattice based model where the solvent molecules, the polymer as well as the polymer solution that forms. So, all these three cases are considered to be on a lattice. And as a key assumption here is that for describing the arrangement of solvent molecules, pure solvent molecules as well as pure polymer molecules and the polymer solution, for all these three cases the same kind of lattice is used in Flory-Huggins theory. Apart from that, we consider no volume change of mixing. So, the fact that the same identical lattice is considered for the two components as well as for the solution, that itself leads to the fact that there is no volume change of mixing associated. So, volume change of mixing is assumed to be 0 in Flory-Huggins theory. Another at least during the derivation, the assumption is that all polymer molecules that are being considered have the same number of segments. So, all polymer molecules have the same size and they are monodisperse. Towards the end of today's lecture, we will see that even for polydisperse samples, the equations can be applied with only very slight modification. but the derivation that will carry out, that's initially only for monodispersed sample polymers with identical number of segments. The other assumption is that within a polymer chain the self intersections are allowed. So, so if we have a different polymer chains, then their segments need not intersect, but for given polymer chains, intersection between different segments of that same polymer chain, that is self intersections, that are allowed. And this is basically the way in which the different configurations or conformations of the system are counted for calculating entropy change, the combinatorial entropy change. During that, the way in the last lecture we discussed that one by one the polymer molecules are introduced in the lattice until all the polymer molecules occupy positions on the lattice, and then the solvent molecules are filled in, and this is the approach used to calculate the different number of distinguishable arrangements possible, which can be used to calculate the entropy and entropy change. So, during that process of introducing the polymer molecules one by one, and for each polymer molecule introducing the segment one by one on the lattice, there the self intersection between segments of the same polymer chain are neglected. That's so that's one of the one more assumption of this theory. And one of the other assumptions is that the polymer segment and the solvent molecule have the same size. So, a given polymer segment essentially is defined based on the fact that it should have the same size or same volume as a solvent molecule. So, after that, finally, one of the key assumptions and limitations of this theory is the mean field approximation, which we also discussed in the previous lecture, where when the polymer chains are being introduced onto the lattice, it is assumed that when a new segment or a new polymer chain is being added to the lattice, the already added polymer segments are uniformly distributed across the entire lattice. So, that is what is called the mean field approximation. And if we, let us say, have a concentrated polymer solution, then this assumption is not that bad, it is okay. But if we have a dilute solution, in that case this assumption is quite limiting, because it is a very poor assumption for a dilute solution. So, through these couple of cartoons, let us just see why this mean field approximation is not a good assumption for dilute solutions. So, for this concentrated solution that we have drawn here, this rough cartoon, one can see the polymer chains are packed quite closely to each other, and they are entangled with each other as well. So, here one can safely say that the segments, that polymer segment distribution across the entire volume of the solution that is shown, that is relatively uniform. So, the making the mean field approximation here will not actually lead to significant error. Whereas, if we look at the dilute solution case, here what we have is polymer chains which are isolated and well separated from each other. So, in the solution we have polymer chains occupying certain volumes, but much of the volume of the solution is occupied by solvent molecules. So, in this case, assuming that the polymer segments are uniformly distributed throughout, that is a poor assumption, because if we consider, let us say, these regions of volume here. So, in these regions actually there are no polymer molecules present, so no polymer segments are present as well. So, assuming that polymer molecules are uniformly present, that is the mean field approximation, is not a very good assumption for a dilute solution case. Next, let us just briefly summarize the combinatorial term, the combinatorial entropy term that we discussed in the previous lecture, and after we summarize and that, then we will move on to the contact term and further on. So, in the previous lecture, if as a first step, we assume that the mixing is athermal, which means that there is no enthalpy change associated with the mixing of polymer and the solvent, and this athermal mixing is an initial assumption. We will see that when we discuss the contact term, there this the athermal mixing, that part, that assumption will be relaxed. But for calculating the combinatorial entropy, which is purely based on the different number of conformations that the polymer chains can adopt. So, for calculating that term, this assumption of no enthalpy change of mixing, or essentially no interactions, that is made. So, with a thermal mixing assumption initially, we developed the combinatorial entropy term to be what's shown here. So, we saw that although the steps involved large number of mathematical manipulations, but finally the expression that we get is quite simple. So, the entropy change, the combinatorial entropy change of mixing is just minus R N1 ln phi 1 plus N2 ln phi 2, where phi 1 and phi 2 are the respective volume fractions of the solvent and the polymer in the solution. So, in terms of the number of molecules of the solvent present, which is N1, and the number of molecules of the polymer present, which is N2, and also the number of segments per polymer chain, which is this X. So, in terms of these, one can define these volume fractions, and these volume fractions basically are what appear in the combinatorial entropy term. If we contrast this with the expression for ideal solution, which we also developed initially in the previous lecture, we see that the two equations are very similar in form. The only difference is that in the ideal solution case, the mole fractions appear here and here, whereas for the polymer solution case, in the case of a thermal mixing, the volume fractions appear in these two places. So, that is the only difference, but as we will see, this difference itself actually can lead to large difference in the value of the entropy change that is calculated using these two equations. So, one additional point here is that the expression that we have here, this will reduce to the ideal solution expression, which is here in the limit when this x equal to 1, which is quite obvious. So, when x is equal to 1, which means the number of segments in the polymer chain is 1, it means that the solute, which the solute actually is now a simple molecule which has the same identical size as the solvent. So, in that case, of course, we should be able to get back the ideal solution expression from the polymer expression that we have developed here. And if you substitute x equal to 1 in these equations here, you will see that the ideal solution expression for delta S is obtained. So, let's just quickly have a look at this combinatorial entropy term a bit more in terms of some numbers and examples, just to get a feel of how the presence of these volume fractions instead of mole fractions, how that leads to a much different value of the entropy change that will be there. So, one thing about the polymer chains or polymer molecules as solute is that even if they are present in very low mole fractions, so even if the number of polymer molecules is small compared to the number of solvent molecules, even then because the size of a polymer molecule is very large compared to a solvent molecule, the volume fractions of the polymer molecules or the polymer in the solution will be significant, or even though its mole fraction is small. So, let us consider an example here. So, let us say we have a system which contains 98 solvent molecules and 2 polymer molecules, just to make it a round number of 100. So, we have this system, and let us say that each polymer molecule, which is a chain like molecule, contains 100 connected segments. So, in this case the N1 is 98, N2 is 2, and X, which is the number of segments per polymer molecule, that is 100. Now, let us first calculate the mole fractions. So, the mole fraction x1, which is just N1 by N1 plus N2, that comes out to 0.98 for the solvent, and x2, which is the mole fraction for the polymer, that of course will be 1 minus x1, which is 0.02. So, we have a binary mixture here. So, x1 plus x2, the sum of mole fractions will be 1. So, x2 will be 1 minus x1, which is 0.02. Next, let us calculate the volume fractions. So, the volume fraction phi 1 is given by N1 divided by N1 plus x N2. So, we see that because the value of x is 100, because of that the volume fraction of solvent is now 0.33. So, although the mole fraction is 0.98, the volume fraction we see is actually 0.33 only. And so, the volume fraction of the polymer, which is phi 2, will be 1 minus phi 1, which is 0.67. So, again volume fraction also, the sum of volume fractions will be 1. So, phi 2 will be 1 minus phi 1 for this binary mixture. And finally, let us do the calculations for ideal entropy and then the combinatorial entropy that we get from Flory-Huggins theory. So, for the ideal entropy case, if we do a calculation based on the equation for ideal entropy change or entropy change for ideal solution, then we get this number 9.8 kb for this particular case, where kb is the Boltzmann constant, And if we use this calculation for a polymer solution, it will be an incorrect calculation, it will give an incorrect result as well. So, this for a polymer solution, this is not the correct result. For a polymer solution, because the polymer chains are long and connected to each other, the correct expression to use is the combinatorial entropy term derived for the Flory-Huggins theory. And if we do the calculation using that equation for the Flory-Huggins combinatorial entropy term, it comes out to be 109.45 kb, which is the correct, which will be the correct value for a polymer solution. So, we see that the presence of volume fractions in this Flory-Huggins expression for combinatorial entropy, that actually leads to, in this particular case, an order of magnitude increase in the actual entropy that change that is happening compared to what we will get if we had an ideal solution. So, with that summary of what we covered in the last class and an example to illustrate the points, let us move on to the other contribution to this in this Flory-Huggins theory, and that is due to the intermolecular interactions. So, in the first part we calculated the entropy change, which was purely combinatorial in the sense that there no effect of any interactions was considered, and only because the polymer chains are long and connected and can adopt multiple conformations, only due to this reason many different distinguishable arrangements were possible, and due to that an entropy change of mixing was there, which was the combinatorial term that we discussed previously. Next, now if we so that was athermal mixing. Now, if we consider the effect of intermolecular interactions as well. So, polymer solvent molecules, they will of course have intermolecular interactions, and the interaction between the two need not be of the same type. So, so if we consider intermolecular interactions, then in Flory-Huggins theory, the incorporation of this effect of intermolecular interaction, that will of course be through an enthalpy change of mixing. So, if we have intermolecular interactions present, upon mixing one would expect the enthalpy to change. So, we will have a non-zero enthalpy change of mixing. But apart from that, that will not be the only effect of these intermolecular interactions. Apart from a non-zero enthalpy change of mixing, entropy change of mixing will also be affected by the presence of intermolecular interactions. The reason for this is, if we have intermolecular interactions present, that these interactions actually might lead to some kind of ordering or some kind of reduction in the randomness of the arrangement of molecules. So, the presence of interactions can result in some kind of ordering, and that in turn can lead to an additional entropy change apart from the combinatorial entropy change that we already discussed previously. So, this ordering induced by interactions, that is the other effect. Now, in this Flory-Huggins theory, we will consider both these effects together through a single term, which is the Gibbs energy change of mixing through contact interactions. So, we will consider this contact Gibbs energy change of mixing delta GM contact, and in this term both the effects, the enthalpy change of mixing as well as the entropy change due to some kind of ordering in the presence of interactions, both these effects will be captured in this delta GM contact term. So, the one assumption that we are making here is that the interaction, the intermolecular interaction that we are considering, they are limited only up to the distance of first neighbors of the molecules. So, long range interactions we are neglecting. So, in any case, in the absence of any charges in the system, the interactions that are present, typically the van der Waals kind of non-bonded interactions, they are typically short range. So, this is a reasonable assumption for such systems. If you have long range interactions present, then of course, this assumption is not a very good one. But for our case, we will consider only first neighbor interactions, which is a good enough assumption for short range interactions. So, let us talk about the different types of contacts that might be present when we form this polymer solution, which contains solvent molecules as well as polymer molecules, which in turn are composed of polymer segments. So, we can have solvent-solvent contact, where two solvent molecules are close to each other and they are interacting with each other. We can have segment-segment contact, where two different polymer segments are close to each other and they are interacting with each other through non-bonded interactions. So, here we are not considering two segments which are let us say directly bonded to each other along a given polymer chain. We are considering segments which are essentially not directly bonded to each other and interacting through non-bonded interactions. So, we can have this segment contact interactions. Apart from that, we can also have a solvent segment interaction. So, a given polymer segment might be surrounded by solvent molecules. So, those interactions those contacts will lead to some kind of interaction which we will call the solvent segment interaction. So, so the Gibbs free energy associated with these three types of interactions, let us represent them by small g11, small g22 for the solvent and segment contact interactions. And for the solvent segment interaction, let us say the corresponding Gibbs free energy of this contact is g12, and these all these quantities are for single contacts. So, for a single solvent contact, the corresponding Gibbs energy let us say is g11, for a single solvent segment contact let us say it is g12 and so on. Now, let us look at this the contacts in a bit more detail, and what happens when this a pure solvent and a pure polymer is mixed together, what happens to the contacts, how new contacts form and old contacts are disrupted. So, for the formation of two segment solvent contacts, so two contacts between points between solvent molecules and segment polymer segment, for formation of two such contacts, one solvent contact on an average will break and one segment contact will break. So, so if we consider let us say a pure solvent and focus on two solvent molecules, these two, and if we consider again a pure polymer here and consider the contact interaction between two polymer segments represented by these orange circles here. So, initially in the pure species we will have in the solvent we will have solvent interactions only, in the pure polymer we will have only segment interactions. Now, let us say, and we are focusing on one solvent interaction here and one polymer segment interaction here. Now, let us say when we mix the two and atom positions get rearranged and we get situation like this. So, here now if we see in this polymer solution that has now formed, we have formed two contacts and both of these are segment solvent contact. So, one solvent contact got broken, one segment contact got broken, and two new solvent segment contacts got formed. So, that is based on this observation, one can basically define the Gibbs free energy change for the formation of a single solvent segment contact. So, that can be defined through the equation that is written here. So, this delta G12 that is equal to G12 minus half of G11 plus G22, and this factor half comes because two solvent segment contacts form when one solvent and one segment contacts get broken. So, the corresponding Gibbs energy change will be given by the expression here. Now, let us say that the number of such solvent segment contacts is P12 in the entire solution that has formed. So, so the total Gibbs energy change, the total contact Gibbs energy change of mixing will simply be given by the product of this P12 times this delta of this small g12. So, this P12 is the total number of solvent segment contacts present in the entire solution, and the delta G12 is the Gibbs energy change associated with the formation of a single solvent segment contact. So, their product will actually give the entire Gibbs energy change contact term for the Gibbs energy change of mixing. So, we have this expression here. Now, let us see if we can come up with an expression for this quantity P12, which is the total number of segment solvent contacts in our polymer solution. So, for that let us start by considering a single polymer or focusing on a given polymer chain in our lattice. So, for a given polymer chain, if we count the number of lattice cells that are adjacent or neighboring to this polymer chain, then that counting can be done in the following manner. So, we will have two terms. The first term here, the term here, this basically this product corresponds to segments of polymer chain that are not at the chain ends. So, all the polymer segments which are not chain ends. So, if we have total x segments in a given polymer molecule, then in that case the number of segments which are not chain ends will be x minus 2, because we are considering only linear polymers which will have 2 chain ends. So, if we remove those 2 chain ends, do not consider that for this term, then we will have x minus 2 segments, and each of these x minus 2 segments will have z minus 2 adjacent lattice cells to them. Now, this z minus 2 comes because of the fact that for a given polymer segment which is not a chain end, it will be connected to 2 other polymer segments. So, if we have this one polymer segment, it will be connected in to a next polymer segment here and a previous polymer segment. So, if the overall coordination of the lattice is z, which means the total number of nearest neighbors is z for a given polymer segment, then 2 of those positions are already occupied by the 2 segments that are bonded to the segment that we are considering. So, if we subtract that 2, then z minus 2 number of cells, lattice cells around this segment are the adjacent cells which are available for occupation by solvent molecules as well as segments from other polymer chains or more distant polymer segments in the same chain as well. So, this z minus 2 is because of that, and x minus 2 is because we have x minus 2 such segments, plus we have another term accounting for the contribution from the chain ends. So, we have 2 chain ends because we are considering linear polymers. So, for each chain end actually is connected only to one more segment, the previous segment along the chain. Okay, so, if we have this as a chain end, this will be connected to one segment here, but on the other side there will not be any connection. So, if the overall coordination of the lattice is z, then z minus 1 adjacent sites will be again available for occupation by other solvent molecules or other segments, and only this one segment which is to which this chain end is connected, that cell is not available. So, for chain ends, the 2 chain ends will have, for each of them will have z minus 1 adjacent lattice cells available. Now, if we simplify this expression, what we get is this z minus 2 times x plus 2. Now, if the x is large, so for long polymer chains typically the value of x will be quite large. So, for large x, this 2, this plus 2 here, that can be neglected, and we can just say that the total number of lattice cells adjacent to a given polymer molecule is just z minus 2 times x. Okay. So, now proceeding from here, now if we know that the total number of polymer molecules in the solution is N2. So, if for a given polymer molecule we have z minus 2 times x number of adjacent lattice cells, then for all the N2 polymer molecules together, the number of adjacent lattice cells that we can get is just N2 multiplied by z minus 2 times x. Okay. So, now this gives the total number of adjacent cells for all polymer molecules. Our aim is to come up with a number for the contact interactions, how many contacts are there, solvent segment contacts are there. So, if this is the total number of adjacent cells for polymer molecules, then we need to next find out how many of these cells are actually occupied by solvent molecules, and that number will give us the total number of segment solvent contact present in the solution. So, to do that, again the mean field approximation is invoked in this Flory-Higgins theory. So, mean field approximation, what it is implying is that the overall volume fraction of the solvent in the entire solution, that same volume fraction can be used to calculate the number of cells adjacent to given polymer molecules which will be occupied by solvents. So, if we have a bunch of polymer molecules and we have identified the neighboring cells or adjacent cells, then some of them will be occupied by solvent molecules, some others can be occupied by other polymer segments as well. So, using mean field approximation, what we say is that out of these adjacent cells, the phi 1 fraction of these adjacent cells will be occupied by solvent molecules only. So, that leads to an expression for this quantity P12, and if we then just try to simplify this expression further. So, we have this N2 times x times phi 1, these 3 terms appearing in the expression for P12. So, phi 1 we can write in this manner, and then we can take this the N1 out, and the x N2 we can take here. So, just rearranging we get this expression, and this quantity, this ratio is nothing but phi 2. So, essentially N2 times x times phi 1, that can be simplified to N1 times phi 2. So, now again based on this simplification, the expression for P12 becomes z minus 2 N1 times phi 2. So, once we have an expression for P12, we can plug that back into the expression for the contact Gibbs energy change of mixing. So, the contact Gibbs energy change of mixing is given by this expression P12 by this. So, combining these two, the expression for the contact Gibbs energy change of mixing is z minus 2 N1 phi 2 times this delta G12 term. So, what in this theory what's done next is the details of the lattice which are contained here. So, this z is a lattice coordination number, so that contains details of the lattice that is being used. So, that term as well as this delta G12, which is the Gibbs energy change associated with the formation of solvent segment contact. So, these terms are basically combined into a single parameter, and that parameter is called the chi parameter or the Flory-Huggins polymer solvent interaction parameter. So, this parameter is defined in this manner. So, z minus 2 times delta G12 just divided by kBt. So, we see that both the details of the lattice contained in the coordination number z as well as the delta G12 term, both of these terms are subsumed or combined to in this Flory-Huggins interaction parameter term, which is also called the chi parameter. And this chi parameter basically is a measure of the polymer solvent interactions. Okay, so next, now if once we have this chi parameter defined, if we substitute this in the expression for the contact Gibbs free energy of mixing, then we will get an expression like this. So, delta Gm contact is just RT times N1 phi 2 chi. So, let us just look at this chi parameter in little bit more detail here. So, this chi parameter can in general be expressed as in the form of A plus B by T, where A and B are independent of temperature. So, we see that this chi parameter is a temperature dependent dimensionless quantity, and the temperature dependence normally can be expressed as A plus B by T. The chi parameter, if we see here, it contains this delta G12 term. So, inside it the chi parameter contains both an entropic contribution as well as an enthalpic contribution, because the Gibbs free energy of course will contain both these terms. So, one can also think of chi parameter as consisting of an enthalpic contribution chi h plus an entropic contribution chi s, and it can be shown based on the discussion that we have been having. It can be shown that this chi h, the enthalpic contribution, that is given by minus t times this partial derivative del chi del t, and when applied to this formula, that leads to just B by T. So, the enthalpic term is the one which is temperature dependent, and that can be shown to be equivalent to B by T. Similarly, the entropic term that will be given by the partial derivative of T times chi with respect to temperature, and that will simply be the parameter A from this expression. So, we see that this the entropic term is actually does not come out to be a temperature dependent term, it is an enthalpic term that is temperature dependent. Now, now that we have defined the Flory-Huggins interaction parameter and used that to come up with an expression for the contact Gibbs energy change of mixing, and the fact that we have already developed an expression for the combinatorial entropy change of mixing, now we can combine both these terms to get the overall Gibbs free energy change of mixing associated with the formation of polymer solutions. So, the combinatorial contribution to the Gibbs free energy change, that will just be minus T times the entropy change of the combinatorial entropy change. So, that if we substitute the expression for the combinatorial entropy change that we have developed earlier, that this comes out to be RT times N1 ln phi 1 plus N2 ln phi 2. Similarly, the other contribution due to the interaction or intermolecular interactions, that is this contact Gibbs energy change of mixing, and that we just saw is RT N1 phi 2 chi. So, we combine these two to get the Gibbs energy change of mixing for polymer solutions, and that expression by combining these two terms. We can get this expression here. So, RT, we will see RT is common to both these. So, we can take this RT term outside, and the final expression for the Flory-Huggins equation for the Gibbs energy change of mixing, that is given by RT N1 ln phi 1 plus N2 ln phi 2 plus N1 phi 2 chi. So, this is the expression, the key expression for the Flory-Huggins theory, and that gives the Gibbs energy change of mixing. And this Gibbs energy change of mixing is a very important quantity for describing the phase behavior of solutions, because starting from here many other quantities can be calculated which are related to phase behavior of polymer solutions. So, let us now that we have developed the complete Flory-Huggins equation, let us just briefly discuss some of the features of this equation as well as some of its limitations. So, Flory-Huggins theory, the good thing about it is that it is a relatively simple theory and simple expression that we get here, but can still qualitatively describe a lot of different kinds of behavior. So, the equilibrium thermodynamic properties of polymer solutions, the qualitative trends it can predict well. Similarly, the phase separation behavior. So, if we have a polymer solution where the interactions are not good and phase separation occurs, so that phase separation behavior, which again is connected to fractionation as well. So, these kind of behaviors are also qualitatively well described by Flory-Huggins theory. And swelling of network polymers, that is also something that Flory-Huggins theory describes well. There are other applications as well, but these are the important ones. Next, let us talk about some of the limitations of Flory-Huggins theory. So, it is a simple theory, and so of course, there will be some limitations. So, one thing, the one obvious limitation is that it predicts the qualitative trends well for a lot of different cases, but it does not give good quantitative agreement with experimental data in general. While calculating the combinatorial entropy term in this theory, the self intersection of polymer segments is actually allowed, which is not a realistic assumption. As we have discussed many times already, the mean field approximation is probably one of the more important weaknesses of this theory, and it's more apparent for the case of dilute polymer solutions, where the assumption of uniform presence of polymer segments is actually not valid much. So, it is not satisfactory for dilute solutions. The chi parameter that we have defined, it is not a very simple parameter. It depends on Gibbs energy change of contact formations and contains entropic as well as enthalpy contributions. So, it is not a simple parameter, and in some cases it is actually also shown to be dependent on the polymer volume fraction or concentration. So, that is another limitation. Apart from this, the fact that the same lattice is being used for the solvent, the polymer, as well as the solution that is formed. So, that itself is a kind of a limiting assumption. So, and it is something that need not be true for many cases. So, these are some of the limitations of Flory-Huggins theory, but that does not mean that this theory is not very useful. In fact, the point of time when this theory basically was developed, this was a landmark development in the field of polymer solution thermodynamics. And even now the theory actually gives a very good qualitative description of various trends related to the behavior of polymer solutions. So, it is a relatively simple but quite good theory, and even the more sophisticated theories that have been developed later on, many of them actually use Flory-Huggins theory as a starting point and then further refine it to get better predictions and agreement with data. So, so now that we have developed the Flory-Huggins equation and talked about the Flory-Huggins equation and the theory in some detail, let us see how we can extract some useful thermodynamic quantities from the equations that we have developed till now. So, before we move on, let me introduce this concept of partial molar properties. So, those of you who have taken courses in chemical thermodynamics, you will be well familiar with this term. So, partial molar property of a given component in a solution is basically a measure of how much a given property will change or a given solution property will change when a very small amount of a certain component is added to that solution. So, let us say if we are talking about any property represented by Z. Okay. So, this Z that we have here, it can be the Gibbs energy, the enthalpy, the volume, any thermodynamic property of interest. So, the corresponding partial molar property is given by Z I bar, that is the representation, and it is defined as the partial derivative of Z with respect to Ni, which is the number of moles of this component I, keeping the temperature, pressure and the number of moles of all other components in the system constant. Okay. So, it basically, as I just mentioned, is a measure of how much a certain property changes when we add a very small amount of a certain component to the solution or mixture. So, the partial molar property that is of most interest to us is what is called the chemical potential, which we will represent by mu I, and this chemical potential is nothing but the partial molar Gibbs free energy. So, the change in Gibbs free energy as of a given solution associated with the addition of a very small amount of certain component, that change basically is what this what this chemical potential of that component signifies. So, since it is a partial molar Gibbs energy, mathematically one can define it like this, and from here another important expression that is of interest to us is basically the relation between this chemical potential and activity of a solution or activity of a given component in a solution. So, this activity is related to chemical potential through the expression here, which states that mu I minus mu I naught is equal to RT ln AI. Here mu I is of course the chemical potential of component I in the solution, AI is the activity of component I in the solution. Mu I naught is the chemical potential of component I in its standard state. So, in general the standard state will be if we have a liquid, then the standard state can be the particular component in its pure state, okay, at the same conditions as the solution is at. So, mu I naught is the standard state chemical potential of component I. Now, this mu I minus mu I naught, which is equal to RT ln AI, this is actually also a partial molar property, and it is a partial molar property of the Gibbs energy change of mixing. So, this mu I minus mu I naught can be shown to be the partial molar Gibbs energy change of mixing, and again mathematically we can define it like this. Now, if we use the Flory-Huggins equation that we have developed for the Gibbs energy change of mixing for a polymer solution. So, the equations that we have discussed till now for the partial molar property, the chemical potential, the activity, those equations are general thermodynamic equations valid for any kind of solution. Now, if we consider the specific case of a polymer solution, then the Gibbs energy change of mixing we can describe by the Flory-Huggins equation here. So, if we substitute this expression here, then we can come up with an equation for the chemical potential of any component I. So, let us focus on the solvent phase. So, for the polymer solution that we have a binary mixture of a polymer and a solvent. So, let us first consider the solvent phase, which is component 1. So, for that this mu I minus mu I naught, if we consider I equal to 1 for the solvent, then we get mu 1 minus mu 1 naught equal to this partial molar Gibbs free energy of mixing, and we can substitute the Flory-Huggins equation here and then carry out the differentiation to obtain an expression. So, in the next couple of slides, let us walk through this derivation step by step. So, next the mu 1 minus mu 1 naught by RT, this quantity here, that basically if we split or expand this partial derivative into multiple terms, then if we are taking first the partial derivative of this term n1 ln phi 1 with respect to del n1, then using product rule we will get these two terms. Okay. So, the partial derivative of this term actually leads to these two terms here. Then the partial derivative of this second term here, if we take the partial derivative with respect to n1, then we will get only this one term. The reason for this is, in taking this partial derivative, the n2 is considered to be maintained constant. So, while taking the derivative, n2 can be taken outside and only this ln phi 2 the derivative ln phi 2 with respect to n1 has to be taken. And in the third again we have n1 and phi 2, both of which will contribute to the partial derivative with respect to n1. So again using product rule, chi we are assuming to be this Flory-Higgins interaction parameter chi will assume to be independent of n1. So in that case by product rule again we will get these two terms as a result of differentiation of this third term here. Now in the next slide again look at all the terms that we have in more detail. So this is the expression that we got by expanding and applying product rule and taking the partial derivative with respect to n1 for the different terms in the Flory-Higgins equation. Next let us consider some of the derivatives that are still here part by part or one by one. So let us consider this term first. So this term del ln phi 1 by del n1 again that we can write in this form, del ln phi by del phi 1 multiplied by del phi 1 by del ln n1. So this derivative is nothing but 1 by phi 1, that is the standard derivative formula for when you are taking log the derivative of a log of something, and this second term will remain here. Now again let us look at the second term, this one in more detail. For that let us to evaluate this term here, we first need to know how phi 1 the volume fraction of a solvent depends on n1. So phi 1 is defined as capital N1 by capital N1 plus x times capital N2, that is the volume fraction of the solvent, and in terms of the number of moles we can just write phi 1 in this form, and that can be done by just converting the number of molecules here to number of moles by applying the Avogadro constant as the factor, and that Avogadro constant will cancel in both the numerator and the denominator, and you will just get this expression for phi 1. So now that we have this expression for phi 1, we can differentiate that with respect to n1, and this derivative upon differentiation will lead to two terms, and these two terms actually can be combined into this single term here. So we have this single term, and we see that this single term that we have can be further simplified, but before doing that let us go back to this term. Okay, so this is a term that we actually need. So this term is just 1 over phi 1 multiplied by this derivative here. So that derivative is shown here, which is this term. So if you multiply this by 1 over phi 1, then we will get this equation which will give the partial derivative of ln phi 1 with respect to n1. Okay. So now we know that phi 1 itself is defined as n1 by n1 plus x n2. If we substitute that here, then upon simplification we just end up with this ratio phi 2 by n1, that's the partial derivative of ln phi 1 with respect to n1. So we see that after mathematical manipulations and simplification we get a quite simple expression for this partial derivative. Okay, so now let us consider the second term, the second partial derivative, which is del ln phi 2 by del n1. So for this again the similar approach as what we did for the del ln phi 1 del n1 term in the previous slide, the same approach can be used, and finally the partial derivative can be expressed as 1 over phi 2 del of phi 2 del n1. So next to evaluate this partial derivative, let us see how phi 2 depends on n1. So that again based on a definition of phi 2 in terms of number of molecules, the same can be converted to the number of moles, and the expression that we get is this here. So now that we have this expression for phi 2, we will try to differentiate that with respect to n1, and the partial derivative that we get here upon simplification is just phi 2 over minus of phi 2 over n1 plus x n2. Now if this partial derivative expression is substituted here, then we will get an expression for this partial derivative as well. So substituting that, so we get 1 over phi 2 this partial derivative, which is here. So upon simplification the expression that we get is minus of 1 over n1 plus x n2, and that is the expression for partial derivative of natural log of phi 2 with respect to n 1. So, we see that we have both these derivatives, partial derivatives that we have, these two terms, for both of them we have defined or come up with simplified expressions. So, for this partial derivative we have this expression here, and this partial derivative we have this expression here. So, next if we consider again the complete expression, we have three partial derivative terms in this expression, this as well as this one, and we have already come up with expression, simplified expressions for all of these, and the corresponding simplified expression for this one is here. For this term we have this expression, and for the last partial derivative we have this expression here. So, if you substitute all of these in the original equation, this equation, if you substitute all these three terms, we get this equation here, and again we'll need to simplify a bit. So, from this equation which is obtained by substitution, if we simplify, so let us go again term by term. So, this term of course becomes just phi 2, because n1 these will cancel. Ln phi 1 let us leave it as it is. This term here, this term becomes phi 2 by x, because if you look at this term here, this is n2 by n1 plus x n2, and we know that phi 2 is x times n2 by n1 plus x n2. So, this term can simply be represented as phi 2 by x. Fourth term again we are leaving as it is, and this last term here, this ratio in this term, this n1 by n1 plus x n2, we know that this ratio is just a definition of phi 1. So, the last term becomes phi 1 times chi parameter times phi 2. So, in the next step we can combine these two terms, because phi 2 is common. So, these two by combining becomes phi 2 1 minus 1 by x 1 here. This ln phi 1 is the ln phi 1 that we have here, and the last term again from these two terms, this phi 2 chi can be taken common outside. So, we get 1 minus phi 1, this one here. Now, this 1 minus phi 1, it is a binary mixture. So, 1 minus phi 1 will be simply be phi 2. So, the final expression where this 1 minus phi 1, this is nothing but phi 2. So, based on that, the final expression that we get for mu 1 minus mu 1 naught is RT ln phi 1 plus phi 2 times 1 minus 1 by x plus chi times phi 2 square. So, for that is the expression that we have developed for the solvent using Flory-Huggins theory or Flory-Huggins equation, and we know that this chemical potential difference is related to the activity. So, this ln A1 we know is just given by mu 1 minus mu 1 naught by RT. So, the ln of the activity of solvent, that will be given by this expression here. Now, the activity of any component A1 can also be represented as a product of its mole fraction x1 and what is called the activity coefficient gamma 1. So, this gamma I, these are referred to as activity coefficient, and these are basically quantities which connect the activity to the mole fraction. So, any activity AI is simply gamma I times xi. So, we see that both the activity as well as activity coefficients can be obtained from this whole expression here for the solvent. Similarly, we can do a similar kind of derivation for the polymer as well, which we have not shown, but doing that similar kind of derivation following similar steps, one can get for the polymer this expression, and again the activity and activity coefficient can be obtained from the chemical potential difference, and that comes out to be what is shown here. And if one wishes to just consider the chemical potential or activity chemical potential on per segment basis, so this is for entire polymer molecules. If we are considering, let us say chemical potential per segment, then we can just consider this and divide that by the number of segments x per molecule. So, that will give us an expression like this on a per segment basis. So, one last point to discuss here before concluding is that all the expressions that we have here, it is fine if we have a monodispersed polymer sample. So, if we have polymers where all the chains are of the same length, have the same number of segments, for that all these expressions are fine, but usually we will have polydispersed samples. So, for polydispersed samples there is not much modification that needs to be done in these equations. The only thing is that the number of segments x for polydispersed samples where the chain lengths multiple different chain lengths of polymers are present. So, for such samples the number average value of this number of segments x has to be taken. Okay. So, this number average x, let us represent that by x n bar, that is simply defined as sigma xi ni by sigma ni, where I cycles or I is the index which runs over all the different sizes of polymer chains that are present in a polydispersed sample. Okay. So, if that is the case, then sigma ni in the denominator that we have here, that sigma ni is nothing but just n2. So, the summation of all the numbers of polymer chains of different lengths, that sum on all the, here we do not have number of polymer chains, here we have the number of moles, but all the number of moles, that summation will simply be equal to the total number of moles of the polymer present in the solution. Okay. So, we see that for a polydispersed sample, wherever the number of segment x appears in any equation, whether it is the definition of volume fraction or the Flory-Higgins equation for Gibbs energy change of mixing or for chemical potential or activity, everywhere if we replace this x by its number average value, then we can apply the same equations for polydispersed samples as well, where the polymer chain lengths can be different. So, we will conclude today's lecture here. So, what we have discussed in the last couple of lectures basically is description of polymer solutions using a lattice based theory, and the theory is referred to as Flory-Higgins theory. So, using that we developed expressions for combinatorial entropy change of mixing as well as the Gibbs energy change of mixing because of the presence of interactions. We combined these two to get the overall Flory-Higgins equations, and that Flory-Higgins equation we have applied to calculate the chemical potential and activity of solvent and polymer in the solution. So, in the next lecture we will continue our discussion of thermodynamics of polymer solutions. We will look at the phase behavior of polymer solutions as well as the solubility of polymers in different solvents. So, what kind of parameters can be defined to quantify or determine how soluble a given polymer is in a certain solvent. So, these kind of discussions will carry forward in the next lecture.